Hi everyone, and welcome to our walkthrough of Module 5, Measures of Association. Evaluating the relationship between variables is one of the basic techniques in data mining. We have a few methods at our disposal, such as distance calculations, measures of independence, and predictive measures. And in this module here, we will learn how to explain distance between data in terms of chi-square, correlation, and cosine similarity. In terms of preparation, we'll be working with our adult data set again, but we'll be using 3 new libraries or new to us libraries, such as scikit-learn, from which we'll be using the cosine similarity function, and we'll be using SciPy, which is the advanced math version or extension of NumPy, and we'll be using the basic Python math package. What does this look like in our setup? Well, first we're going to pull in NumPy, Pandas, and Matplotlib. We already know those. Then we're going to import the math package. And from math specifically, we're going to import the geometric functions and the degrees. So the cosine, acosine, and degrees. And from SciPy, here we're going to import the spatial library, chi-square, and chi-square contingency. And then from sklearn, from scikit-learn, we are going to import the cosine similarity package as well here. So here we're going to read in our adult data set with pd.read_csv, and then we're going to look at the adult data set. In terms of distance measures, we've already come across 2 of them. We've come across the Euclidean distance between 2 vectors or between 2 attributes, which measures the direct distance, that's the distance as the bird flies diagonally, however, right, between 2 attributes. Then we've come across the Manhattan distance, which is the city block distance, in which we can move only horizontally and vertically in order to get from one vector to the next or from one attribute to the next. And now we're going to talk about cosine similarity, which is a little bit different because in cosine similarity, we're not connecting directly between 2 attributes here are 2 vectors, but we're looking at the angle between the 2. And of course, attributes are more similar, that is closer together, if the angle between them is smaller, and they are more different from one another, the larger the angle is between the 2. So how does this work mathematically? For cosine similarity, we can find the similarity between A and B, which is the cosine of theta, which is this angle here, the blue arrow, by generating the dot product of A, the vector A, and the vector B. And we'll look at how to generate a dot product in a little bit. And then we divide that by the vector A multiplied by the vector B. Euclidean distance and Manhattan distance clearly require numeric attributes, and cosine similarity, though, is much more universal. With cosine similarity, we can also measure the distance between words into sentences or even entire documents. And that is why cosine similarity is so popular with text mining efforts. Take these 2 sentences here. We can count how often each word occurs in these sentences. That gives us a vector of each sentence, like this one for sentence 1, and this one for sentence 2. So we take these vectors, we turn them on the side, like this, and then we apply the formula in the yellow box here that says we have to calculate the dot product between the 2 sentences and divide that by the length of the vectors multiplied. So let's do that. We take the dot product first, which means multiplying each value from vector 1 with the corresponding value from vector 2. So 2 times 2 plus 0 times 1 plus 1 times 1 plus 1 times 0, and so on and so on. And that gives us the purple 9 here. Then we calculate the length of each vector, which is basically multiplying each value by itself, and then adding them all up and taking the square root. So here for vector 1, we multiply 2 by times 2 plus 0 times 0 plus 1 times 1 plus 1 times 1, and so on and so on. Then that gives us 12, and we take the square root of that, and that gives us 3.46 here in red. We do the same thing for vector number 2, which is 2 times 2 plus 1 times 1 plus 1 times 1 plus 0 times 0, and so on. And that gives us 10. We take the square root of that, and that is 3.16. So now we can calculate the cosine of these two vectors. That means we apply the formula here, right? Our dot product is the purple 9, and then we divide that by the length of vector 1, which is 3.46, multiplied by the length of vector 2, which is 3.16. That gives us a cosine of 0.823, and the associated angle, that's what we have to look up, gives us 34.6 degrees. So vector 1 and vector 2 have a cosine similarity of 36 degrees. And that's nice, but what does 34.6 degrees really mean? Well, think about it this way. We know that the cosine of 0 degrees is 1, and the cosine of 90 degrees is 0. If the values of two attributes or variables or features or whatever you want to call them are 0 degrees apart, then they're identical. This means that one is a copy of the other with a one-to-one relationship, such as here, sentence 4 and sentence 1. So the bigger the angle, the more the attributes differ from another. If you look at sentence 3 here, you see that no word in it appears in any of the other sentences. In other words, the two vectors could not be any more different from each other. And that's what cosine similarity shows us. So now let's look at what this looks like in Python. We're first going to do a small example, and then we're going to go to the adult data set. So here's a small mathematical example. We have a vector A and a vector B. Our vector A is a NumPy array of 1, 2, 3, and the vector B is a NumPy array of 1, 1, 4. So here are the two vectors here. The first thing we're going to calculate is the dot product. So we're going to use NumPy dot A and B, and that gives us the dot product, which we have now stored in dot. Then we're going to normalize vector A, and that also involves calculating the length of the vector right here. And then we're going to generate the cosine, in which we divide our dot product by norm A multiplied by norm B. So that gives us this cosine here. Now we need to find the angle from that cosine, and in order to do that we require two steps. The first one is we need to convert the angle into radians, and then we need to calculate the degrees from the radians. So to convert the angle into radians, we use our math.acos. That was the library that we pulled in up here, right? And we do that on cosine 1, which we've calculated here. That's this value. And now that we have the angle in radians, we can calculate the degrees from that with math.degrees, and that is the second library that we pulled in here. right? And now we can say, well, math.degrees of the angle in radians, which we have calculated here. So now, here's our cosine again. Here's the angle in radians. And here is now our angle in degrees, 19.110. And that is just the math. So for that, however, we are going to use our packages like sklearn metrics to speed things up considerably. So we'll do that again. So I'm going to use cosine similarity, which I've imported from sklearn metrics up here. There you go. And I'm going to apply that to my vectors A and B. And oh, that gives me an error message. Okay, interesting, right? So let's see what it tells me here. Value error. Expected 2D array got 1D array instead. Array 1, 2, 3. Yeah, we have 1, 2, 3, right? Reshape your data either using array.reshape -1.1 if your data has a single feature, or array.reshape 1 -1 if it contains a single sample. That's a pretty cryptic error. We could now either search Stack Overflow or we could read on. So the whole idea behind the cosine similarity function is that it expects two-dimensional arrays. And the problem is our input data has just one array each. A has this array, B has this array, and that's why we get the error. So now we're going to need to reshape our arrays. Here's how we do that. In order to use the cosine similarity function from sklearn metrics, we need to use dot reshape. So here's how to do that. I'm calling this AA, and it equals a dot reshape, and then we're going to say 1, and then 3, because we have 3 values in our array. So now it will recognize it as a 3-value array. And then we have BA here, which is what I'm calling the second array. And we're going to reshape B with a 1, and also 3 because we have 3 values in our array here, right? 3 values each. So now that I've reshaped my array here, I can calculate my cosine similarity, angle in radians, and degrees the way I did it before. And I can print my values. So here we're seeing the cosine. We already know that one, of course. And here's the angle in radians, and here's the angle in degrees. Now these are the same values that we saw above. That's because the values don't change, only the packages have changed here. And there is a third way in which I can calculate my cosine similarity, and that is with the spatial package from SciPy. So we've seen the straight math way now, we've seen the more elegant way of using sklearn metrics and the cosine similarity. So now we're seeing the third way, which is using the spatial package. And here's how this works. The first array that we're going to set, and I'm going to do this now with the adult.education years, and then we're leaving our little example. So I'm going to say A is my NumPy array, and then I want to see if education years and income USD are related. So the first array I'm building is adult.education years. For B, I'm going to build my array on adult.income USD. And then the result is, and here's how to use the spatial package from SciPy, 1 minus the spatial distance of the cosine of A and B. So now that we have this result here, we need to, again, that gives us our cosine here, our 0.94. And then we're going to have to apply the angle and radians again with the math.acos, and we calculate the degrees from math.degrees. And as you can already see here, as the output shows up when I hover over things here, this is exactly the same output as up here. So we've seen 3 different ways, in other words, of how to calculate cosine similarity in Python. The second technique that we can use in order to figure out how values are associated is chi-square. Now, we've seen that cosine similarity and also our distance measurements really work with numeric values. Even though cosine similarity works with sentences, it reduces the sentences to numeric vectors. So we're with numbers again. But how do we deal with categorical attributes? This is where chi-square comes in. Chi-square works with categorical attributes, does not work with numeric attributes. Well, it works with numeric attributes, but it really doesn't produce anything meaningful with numeric attributes. That's the difference. We've seen that cosine similarity, just like Euclidean and Manhattan distance, operate with numbers, right? Even though cosine similarity, we said, well, we're starting with sentences, but these sentences we then transformed into numeric vectors. Chi-square works differently. Chi-square really works on the basis of categorical attributes. It does not work with numeric attributes. Now, before we step into chi-square, we need to understand that chi-square is based on hypothesis testing. Hypothesis testing always starts with a null hypothesis and an alternative hypothesis. The null hypothesis always tells us whether our basic assumption is that the 2 variables we're comparing are either independent or dependent or equal, and the alternative hypothesis assumes the opposite. At the end of the math that we're doing stands a p-value. That p-value is either greater than 5%, which means that the null hypothesis can be proven true, or the p-value is less than 5%, which means that we cannot prove that the null hypothesis is true, and therefore the alternative hypothesis is more likely. So if chi-square were a meme, that's what it would look like. So when we do a chi-square test, we are interested in determining whether the variables or attributes we're looking at are connected in any which way, or whether any connections that we might suspect exist are in fact due to random chance. Let's take a look at a mathematical case study. Say you work for an internet-based pet supply store named Chewy.com. To understand your customers better and show them contextual ads, you want to know whether they prefer dogs to cats or cats to dogs. In the survey, you also capture their gender because you want to know whether women are more likely to order cat supplies and men to order more dog supplies. The survey results are here. Looks like men do order more dog supplies and women, oh, they order more dog supplies too. But they also order cat supplies. So you do the magic math, and out comes a calculated p-value of 0.043. That's less than 0.05, right? So if 0.05 and a p-value of less than that is the test for dependence, and any value greater than 0.05 shows independence, then this p-value here shows that the variables are dependent, and the results are that men really prefer dogs to cats. How did that happen? Let's talk about the math here. So first of all, we need to understand that chi-square calculations apply, we said that already, right? Only to categorical data, and that the numbers we are using here should be greater than 5. So that was step 0. For step 1, we set up the null hypothesis. H null assumes that our two variables, gender and pet preference, are independent. The alternative hypothesis, or HA, assumes that gender and pet preference are dependent. For independence, we would have to get a p-value of greater than 0.05, and for dependence, we would expect a p-value of less than 0.05. All right, so for step 2, we're going to set up a comparison table, and we're summarizing our values. So note that the sum column holds the additions within each row, and the sum column here holds the additions within each column. And we also calculate the sum of sums. In step 3, we now calculate the expected value for each entry. For that, we're going to multiply each row total by each column total, and then divide by the overall total. That's how we end up with the numbers here. Now we can plug these numbers into the mathematical formula in the orange rectangle here. And the chi-square formula is chi-square equals the sum of all observed minus all expected values squared divided by the expected values. We're going to do that next. All right, so here's the result. In this section of the matrix, we apply this chi-square formula to the results we've previously calculated. That gives us these values. We add them all up, and we use our degrees of freedom to calculate the p-value. A degree of freedom is always the product of rows minus 1 and columns minus 1. You can read up more about this in the materials posted in our class folder. Now that we have our degrees of freedom and our chi-square, we plug it into the chi-square calculator, and out comes the p-value, which is clearly below 5%. And that brings us back to the very beginning, in which we saw that after our magic math, which we've just done, the p-value is 0.043, which is clearly less than 5%, which means that, yes, our values are dependent. Here's what this looks like in Python. We use our chi-square contingency package from SciPy Stats, and we set things up like this. Chi-square, our p-value, our degrees of freedom, and our expected values are equal to our chi-square contingency of the crosstab of, and here we're going back to our adult data set, native country and occupation. And because we want to deal with arrays, we're going to use the values here. Once we've done that, the most elegant way of doing this in Python is to use the chi-square contingency package from SciPy Stats. And the 4 variables that we can capture from chi-square contingency are the chi-square number, the p-value, the degrees of freedom, and we can even capture the expected array, knowing that, yes, these will be all the expected values, so it'll be pretty long. So here's how we set this up. Chi-square contingency of pandas crosstab, and then we're going to our adult data set. We have 2 categorical attributes, namely native country and occupation. So we set this up for adult.nativeCountry and adult.occupation. And we're going to pick the values here as a NumPy data frame array. And that's it. That's the entire chi-square setup right here. And then we can print the contents of these variables, namely the chi-square statistic from chi-square, the p-value from p, and the degrees of freedom from DOF. And if I wanted to see a long output, I can even print the expected values. So here's what we're seeing. The chi-square statistic is this. That doesn't really tell us very much because we need to really look at our p-value, which 3.05. Oh, that looks like it is bigger than 5%, but look at this here at the end, right? This is to the power of e minus, or to the power of 10 minus 227, which means a very, very small number. And we have 574 degrees of freedom. But what this p-value tells me here with this very, very small number is that the attributes of native country and occupation are in fact not independent. Remember, the null hypothesis of chi-square is independence, right? So this p-value shows me that native country and occupation are not independent. In fact, it is more likely that native country and occupation are dependent, specifically that occupation may be dependent on native country. All right, so the third topic today is covariance and correlation. Covariance and correlation are related, and the goal is for both of these to determine if two variables are tightly enough connected that we can detect a pattern to their changes. In other words, we want to see that if one variable changes values, does the other variable also change values? And if so, are those changes related in some way by some sort of function? I encourage you to watch the instructor video in the original file so that you get a better understanding of covariance and of correlation. In a nutshell, covariance looks at the relationship of two variables if one of these variables changes. If an increase in one of the variable results in an increase in the other variable, both variables have a positive covariance, and if both variables decrease, that is also a positive covariance because they both move in the same direction, and that shows up as a positive number. If an increase in one variable causes a decrease in the other, that's a negative covariance. So if they behave opposite to each other or inversely in an inverse relationship, and that then gives you a negative number. Covariance works only with numeric attributes, so we're back to numerics. And we are going to use np dot covariance as the function, and we're going to use education years on income USD in order to see if they increase or decrease together or inversely. So by default, np-cov calculates a sample covariance. To get a population covariance, we're going to set the degrees of freedom to 0 or to set the bias to true. And if you omit the bias, you will calculate the sample variance. What that is explained in this video. So the sample covariance assumes that the degrees of freedom are 1. We are going to set it up like this. np.cov, and then we have the adult.education years as an array and the adult income USD, and then we have the 0 and then the 1 here, and that gives us 33078. Great. Okay, and the population covariance can be calculated by setting the degrees of freedom to 0 here. There you go. So we're seeing that degrees of freedom is automatically by default set to 1. And the population covariance, if we set the bias to true, gives us the same result here. It's just a different way of writing it. And the same covariance is what we get when we omit the bias equals true setting, and that is the same as up here. That gives us the same result for the sample. Now here, the difference is very, very small, so it doesn't really matter whether we are using the sample or the population covariance. in cases where we have more data, it will matter. So what does this really mean though, right? This means here, if our adult education years, if our education year increases by 1, just by 1, the income USD will increase by $33,078.30. So now that we know how covariance behaves, namely we're looking at an increase of 1 in the first attribute, and then we're seeing what the increase or decrease is going to be in the second attribute, let's talk about correlation. Correlation doesn't focus so much about on the increase in value, it focuses on the strength of the connection between the two values. We measure that strength of the connection between the two values with a Pearson correlation coefficient. This Pearson correlation coefficient can lie between 0 and -1. If it lies there, then we say the two attributes are negatively correlated. If the Pearson correlation coefficient falls between 0 and +1, the attributes are positively correlated. We're seeing this down here. Here is a negative correlation, which means as x increases, y decreases. Here we're seeing a positive correlation, which is as x increases, y also increases, sort of, kind of. We're seeing a couple more outliers here. And if our Pearson correlation coefficient is around 0, we're seeing there really isn't any tendency of how the values behave. A perfect negative correlation means our R is -1. A perfect positive correlation is our R, that is the Pearson correlation coefficient, equals +1. All right, so how does this work in Python? Let's see if education years and income USD are connected. For that, we are going to set up our core edUSD attribute here, variable, and here's what we're going to stick into it. We're going to say, well, look at adult education years dot correlate that with adult income USD. And then we're looking at the outcome of that correlation, and it is 0.289745, and so on and so on, which tells me, is a very, very weak positive correlation. So in a way, they are correlated, but really not too much, right? So if you want to plot this with a plot, we use a scatter plot, and that's what you're seeing here. But the real power of the correlation function, the core function that we're using here, is not in correlating just one value to another or one attribute to another, but it really is in setting up a correlation table, and that's what we're seeing right here. So if we say, here's the correlation set, give me all the correlations within the adult data set, and then we look at them, then we're seeing that age is correlated to age with a 1. That's because it's the same value. Same with education years, same with hours per week, same with income USD. Okay, that's not interesting. But we're seeing that education years and age are correlated weakly, but positively. We are seeing that hours per week and age are correlated a little bit less weakly. And we're seeing that income USD and age are correlated even a little bit less weakly. There's more, right? But we're seeing here the strongest correlation is between income and education years. Even if that is just a 0.289, which is a 0.3, we're still seeing that this is the strongest correlation that we have here in our table. And now that we know that, we can also set that up as a heat map. And for that, we are going to use our matplotlib and our plot library here. We're setting up our figure, and we're going to add our subplot. We're going to use the cool, warm colors here. and we are depicting our correlation. That's the outcome here. This is what we're showing down here, right? And we're seeing that we're setting up our ticks here based on the length of the correlation columns, right? The core, this here, and the columns. And we are setting our ticks to a rotation of 90, right here, right? And those are the Y ticks. Here are the X ticks here, right? And the X tick labels and the Y tick labels. So what we're seeing here in our heat map is a perfect correlation. That's the dark red between a variable and itself. And we're seeing a correlation that's a little bit lighter, but still the strongest correlation between income USD and education years, as we've seen above here with the 0.28 that's still highlighted. And then we're seeing some weaker correlations right here. So a heat map can be pretty useful. It gives you a great visual from, especially if you have a number of attributes that you're trying to compare, and you have like lots and lots of numbers here. So this is where a heat map can come in really handy. All right, and now it's your turn to calculate the covariance between hours per week and income USD. Here I'm showing you how to do this. And then the correlation between hours per week and income USD. And I want you to take a look at, well, how this number here really folds into the correlation plot and what the correlation plot tells you, whether hours per week are related with income USD. What do you think? And that's the end of our workbook and the end of our walkthrough. Thank you so much, and I look forward to seeing you in another Tuesday walkthrough.